in the graph.
Yeah, I just thought about when I started again. I told you, like, you have to remind me. And you didn't, so I said,
It's not my life job to remind you of stuff.
no, I know, but never still I'll try to.
All right, let's make a start. Here we go. All right, so quick check-in. How are things going? How are people feeling? Other midterms apart from ours this week? Or other midterm stuff? Yes, no? All right. And generally feeling about this course, things I need to know, things I should change. Okay. All right, well then let's get to it. So it's been pointed out that there are some questions involving Lagrange multipliers on the quiz. So a good thing the quiz is only due on Wednesday, because we're going to calculate them today, Lagrange multipliers. Then we are going to, so this is a very nice application of derivatives, and it kind of will also pull together the stuff that we talked about last week. Then we're going to do the probably expected skip from derivatives to integrals. So we're kind of following the path with functions of many variables that you followed with functions of one variable. We've done about all we can do. Well, that's not true. We could do a lot more on derivatives, but for this course we're not going to. We're going to hop, skip, and a jump into double integrals. So integrals involving functions of two variables. And most of what we're talking about today is going to be delving into those in quite a lot of detail. All right. So, oops, why is my pencil not working? Come on, pencil. All right. So, last week we finished up by talking about how to maximize or minimize functions of two variables or more. And it was basically a similar process to functions of one variable. You just had to do a little bit more because you had to find the Hessian, but it's the same basic idea. You find critical points and then you check, in our case using the Hessian, if you were in one variable just using the second derivative test, that you've got a max or a min, and you move on with your life. Okay. But suppose you have a question like this one. Find the shortest distance from the origin to the curve x squared y plus equals 16. So now, we're not just saying, I don't know, like, minimize the distance. We're not saying minimize that curve, which we could do. And we're also not just saying minimize the distance from the origin to a point, because it's from the origin to a point on a specific curve. So what we've got over here, although you might not see it, is a constrained optimization problem. So if we wanted to write this kind of mathematically, what is the thing that we would want to solve? Well, we want to minimize the distance. So we want to minimize. So what is? So we know that we're we're in x squared y equals 16. So at the moment, we're just thinking in 2 dimensions. So we're thinking about we've got some function x squared y equals 16 on the plane there, and we're wanting to minimize the distance to the curve. What is the distance? How do you work out the distance from the origin to some point P?
It's the square root of x squared plus y squared.
It's square root of x squared plus y squared. And we could say, let's minimize that. But honestly, that looks a little bit hairy with the square root. And we know that if we just minimized x squared plus y squared, that's equivalent to minimizing the root. So we're just going to leave out the root for the moment to make our life simple. But then, what do we have to do? Well, we have to say, this is subject to, and our constraint says we can't just take any x and y. There have to be an x and y that satisfy this equation over here. So subject to x squared y is equal to 16. Yeah.
How do we
just get rid of the root like that.
So we basically just say, okay, I need to minimize the square root of something.
Yeah.
Well, the minimum, the x and the y value that will minimize the square root of x squared plus y squared is the same x and y value that will minimize x squared plus y squared.
And x squared plus y squared is a small number, and then like the smallest number in the root.
So if you look at the two functions, x squared plus y squared and the root of it, they both have a minimum at the same point. So you could totally keep the root in. It's just, it scares me. And it scares apparently a lot of other mathematicians because they do this a lot. Okay, so we are subject to the fact that our x and our y have to lie on the same place, on this curve. Okay.
So this is not a surface.
X squared y equals 16. What is it? Well, I mean, it depends whether you're thinking about it in Z or, I mean, we're just saying, we're actually just, it hasn't said anything about including the Z coordinate, so we're just thinking it's just a, I mean, if you want to draw this, what would you draw? You'd rewrite this as y is equal to 16 over x squared. So what's that? What does that bunny look like? Quick, draw that bunny. Draw it, draw it. Or you could use...
on paper.
Yes, I could. That's
Come on, it's Monday. Stretch your brain.
Monday?
I think it's Monday. Yes. Okay. Okay. Come on, you can totally draw this. Okay. Well, your x values what happens is x gets really close to 0. Well, y must go really positive. What happens is x gets really, really big. We're dividing by something huge, so it must do this. So it must be something like that on that side. Okay, and I know that y is positive because nothing fancy happening here. Over here, what's happening? Well, as x gets really close to 0 from this side, it's getting squared, so we've got the same behavior. As x gets really negative, it's still getting squared and really big, so we're dividing by something big, so we must have something like that. So the point that we're looking for is some point P on here which means that this is the smallest distance of all the possible points that we could take. And having done this quick sketch, you might immediately think, well, this graph is symmetric, so we should find two solutions, because whoever's closest here, that should also be closest. So this is why we sketch. Okay. I'm going to slightly rewrite this because it's going to help us with the technique. So what I'm going to do is I'm going to call this, I'm going to create a new function. So rewriting. I'm going to let g of xy be the function x squared y minus 16. Okay. I can do anything like that. And then I'm going to rewrite this as minimize x squared plus y squared subject to, so we write subject st for subject 2, and then sorry, not 16. Alright, so it's not immediately clear why I would do this, but we'll see when I've explained a little more. So I've just said let g of xy be this function over here. So I've just taken my 16 over, and I'm saying I want to minimize it, this bunny, subject to g of xy equals 0. And if I put a 0 over here, you'll see it's the same thing. Okay, I've just done I'm just, essentially what I'm introducing over here is this g of xy, which we're going to need.
Isn't it wrong to say it this way? Because, for example, if you do x squared plus y squared is equal to 4,
Yeah.
on the 3 dimensions, it's going to be a cylinder.
Yeah.
But if you say g of x of y, don't you introduce a z, therefore a convergence point? Because, for example, with my cylinder example, x squared
Yeah.
plus y squared equals 4. If you do x squared plus y squared minus 4
Yeah.
equals z,
Yeah.
you get a cone, not a cylinder.
Okay. I don't think it's, but I can't picture exactly what you're saying. Maybe ask me afterwards.
Okay.
Okay. All right. So what do we do here? Ta-da! Lagrange multipliers. So we're taking a little step into theory land. I'm just going to talk through the theory and then we're going to apply it. Okay, so what is this? And part of why I'm doing this is because if you are into kind of slightly more formal maths, this is a beautiful theorem. I think it's one of the most delightful theorems that I've ever encountered, and it makes me happy every time. But initially you read it and you're like, what now? Okay, so reading mathematics, how would you do this? Here's a new theorem for you to get to grips with. Remember what we're trying to do. We're trying to find something that satisfies we want to maximize or minimize something subject to some constraints. Okay, so you might have done the simplex method at school or something, things like that. This is an alternative to that. All right, so what do we got? Let's read through this. Suppose that f and g are two functions. Okay, so we've got f of x, y, which is the thing that we want to find the maximum or minimum to, and now you'll see why I rewrote this thing, subject to some equality constraint. Okay, so we've got two functions of two variables, and we want to maximize or minimize one of them, subject to the other one being equal to 0. Okay, what are our assumptions? We're going to suppose that f and g have continuous first partial derivatives, all right, and on some particular level curve of g. So we're just assuming that these are nice, well-behaved functions, and so remember that this is a level curve. Okay, so we're assuming that f and g do their thing, and if you look at specifically that level curve of g, where it's equal to 0, then on that level curve, everything is well-behaved. Okay, so they can do crazy stuff elsewhere, but on that level curve, they behave themselves. And we also suppose that if we only look at that level curve, then on that level curve, our function f of x, which we're interested in, has a local max or min. So that's the key thing that we're assuming. Okay. So we are assuming that our function f of x has a local maximum or minimum value on our level curve of g, which obviously is kind of a necessary assumption because we're assuming we can solve the problem that says minimize subject to being on g. And if it doesn't have a min or max, then we're screwed. So we're assuming that there's a solution and that we can find it. Okay. And finally, we're going to just make some other ideas. So finally, suppose that P naught is not an endpoint of our curve. So we're kind of assuming that we're on our level curve, and we're looking at our point P naught where we have our minimum, and it's not an endpoint. So there's stuff around of the curve either side, and at the point where we've got our local max or min, our gradient is not equal to 0 of our g. Okay. Putting all this together, what does this give us? This says that we can find some number lambda 0 such that this point over here, so now we've suddenly gone into three variables, this point, x0, y0, lambda 0, is a critical point of the Lagrange function, which probably doesn't seem super exciting, but notice what we've done. We've gone from trying to maximize or minimize something subject to a constraint, which we don't know how to do, to just finding a maximum or a minimum of some unconstrained thing, which we totally know how to do. So what this method of Lagrange multipliers does is it takes things that look like this, minimize or maximize subject to, and turns it into a straight min or max problem that is unconstrained, which we know how to solve, by creating this shiny new function called the Lagrange function. What does the Lagrange function look like? It looks pretty straightforward. It has the thing that we're trying to maximize or minimize plus some constant, or some lambda times our constraint. Okay. So although we're going to talk a little bit about the proof, just so that you can kind of see how it might work, and it might kind of tickle your brain a bit, the basic idea behind constrained optimization in multiple dimensions is you take your thing you want to find an extremum for, and you add it to lambda times g of x to create this new bunny over here, and then you simply find a maximum of that, and you're done.
But Lagrange is a 4-dimensional object?
Yep. So, we know how to deal with those.
So we're raising up a dimension?
Yep.
And
So
then
it
we're
turns out
coming
by
back
going
down
up,
again.
yep, going up a dimension and coming back down solves our problem. How cool is that? Isn't that nice? Alright, so I want to talk through the proof very briefly, just so that you can, because it's not clear, I mean this is just a whole bunch of words, and you know, I wouldn't want you to take my word for it. So let's have a look at this. Okay, so the key thing to take out of this is, what are we assuming? Alright, so you wouldn't usually write this in the proof, but I just want us to be clear what we're assuming. Okay, we're assuming that our nice continuity stuff near some p naught on our level curve okay, so that's the first sentence. Okay, so that's nothing particularly crazy here. And this is the strange one. We're going to okay, and then the other things that we have are 1 and 2. I'm not going to rewrite them again. We're assuming that p naught, this point that we're looking at, isn't an endpoint, and also that our gradient at that point of our constraint function is not 0. What can we deduce about this? Okay, so these are just kind of what we need to keep in mind as we work through our proof. Well, what did these bits tell us? Essentially, those bits up there are really just telling us that our curve C, our level curve of g equals 0, is well behaved, that it has a tangent line. That's really what we need these for. You can go back and check your notes, but basically p not being an endpoint obviously means that we don't have to worry about it kind of just like stopping and doing something crazy. And del g equals 0, that tells us that we can find a tangent line there. Okay, so this says so I'm not saying anything particularly interesting. What is the picture that we want to have? Here's my curve C. Whoops. Here's the point P, and I'm just saying that C is well enough behaved that I definitely have a tangent line, and because my gradient of G is not equal to 0, it will be normal to that. Okay. So this is all stuff that we saw last week. Okay.
And why do I need my gradient to not be zero with my constraint?
Because then I wouldn't be able, because if it's 0, then I wouldn't have the fact that it's normal, because it would be 0, it's not normal to anything.
Okay, so I need those two.
Yeah, so for what we're going to do, this all falls apart if the gradient of our constraint is 0 at that point. Then you have to use another method. But generally speaking, it's going to be okay. Okay, so there are assumptions that we make in this. They're not too onerous, but there are other methods to deal with. Yeah.
Isn't saying that it is continuous near that point then redundant, or do we still need that?
So we need the continuity stuff, plus so the continuity isn't strong enough. Oh, sorry. So the continuity is for our derivatives.
Oh, right, yeah.
Yeah. All right. So we've dealt with our curve, our level curve of G and our gradient of G. Now what can we say about F? So what we're going to do is kind of a proof by contradiction, which is always fun. So where we want to go, the goal of this is okay, so the crazy thing where we want to go is we want to show that our gradient of f at this point p naught is parallel to our gradient of g, because that's going to be helpful. How do we do this? We start by saying, okay, suppose it's not. So suppose that our gradient of f is pointing in some other direction than del g. And we're going to arrive at a contradiction, conclude that this must be the case, and then we're almost home free because we're going to create our Lagrange from the fact that the two vectors are parallel. All right. So suppose that our gradient is not parallel to the gradient of our constraint function. What can we say? Well, if our gradient is not parallel, so it's not pointing in the direction of del g, then it must be pointing in some other direction. Okay, so it's pointing in some, we have some, then we must have a component of our gradient of f that points along the tangent line. So we can find a component of del f, say v, that points along there. Okay, happy with this so far? Okay, then what happens? Well, now we can talk about the directional derivative in the direction of v. Because obviously we're going to talk about directional derivatives because we're bringing in everything from last week. Okay, so if we look at the directional derivative, what can we say about it?
It's non-zero.
It's non-zero. Okay, so let me just get this written down. So if we look at what happens as we kind of look at little areas on either side of this point P naught that we're interested in, as we move away, then as we move in the direction of our v, then our f of xy will increase. Sorry. As we move, yeah. Okay, so I'm just thinking first to explain this. Remember what our directional derivative says. Directional derivative says if you go in this direction, you are increasing your function. If you go in that direction, you're decreasing your function. Okay, so looking at this, we say that, okay, if we move away from p, our function increases. And in fact, if we move towards p from this side, our function increases. But that's a problem, because if you think about what we said at the beginning that we assumed that there was a maximum or a minimum at p0 of our f. But now we've just said that there isn't, because you'll move here, increase this way, and then keep increasing this way. Whereas in order to have a maximum or minimum, you need to increase here and then decrease there. Or increase there and decrease there. So we have a problem. Okay. And therefore, our original assumption that we made, which screwed everything up, was this assumption here. And therefore, del f must be, gradient f must be parallel to gradient of g. Okay, I'll write this up. I'm not going to spend more time on it, but it's kind of a cunning little twisty thing. And if you like this sort of thing, ask me. I'm happy to talk about it for hours.
Doesn't it be very creative to be a mathematician?
Yes. So this was one of the mind-blowing moments for me when I went to grad school in the US, and I was in second year and just trying to learn all this stuff, and someone asked one of the really experienced lecturers he's written so many textbooks, he's really well published, and they said to me, so what is the most important thing for a mathematician? What do you have to know? And he was like, well, the most important thing is to be creative. Okay, so I will write up what I just said, but the conclusion is okay. What does that give us? Why did we want to go through all of this? Well, if our del G is not equal to 0, then we can find some lambda in real numbers such that, okay, this is maxi, but if these two things are parallel, this means that we can find a real number such that this vector is equal to lambda times this vector. Okay. Or equivalently, because it's going to be convenient, minus lambda. Okay? Bear with me, I have one more step, so I'm going to just rewrite that to say that the gradient of this function is equal to 0. Okay, and that is kind of the key thing. We have now said, hana, if f has a local max or min, blah, 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 then this new function is equal to 0 at the point where, well, this gradient is equal to 0 at the point where our f has a max or a min. And there's no constraint here. So all we have to do is to find this point is maximize or minimize this bunny here. That's where we got to. Expanding this out. So I'm going to call this function over here my Lagrangian. Usually with a nice L like that. Okay, so pulling it all together, we conclude that we have this equation here, which we can split out. What does this equation say? This says that each of the components, remember this is a vector equation, each of these components is equal to 0. So it says, take the partial derivative of your shiny new Lagrangian with respect to x, set it equal to 0, set your y, and also, oops, that should not be an x, that should be a lambda. Okay, so because our shiny Lagrangian is now a function of x, y, and lambda, we'll have three partial derivatives, set them all equal to 0, do your max min on your Lagrangian, and if you find that a critical point of your Lagrangian is a max or a min, then that solves your problem. Okay. As I say, if you would like to talk more about this really quite exciting proof, let me know. And if you go into economics, it's all about Lagrange multipliers.
How do you know that it's like if your critical point, what if it's like a minimum function or something? When it's on maximum or minimum?
So, I mean, my point is that. Sorry, ask your question again.
You mentioned that at the max min, there's a, like you could find the critical point, but what if the critical point isn't the maximum or minimum, like a point of inflection? Because there's different critical points than just maximum and minimum.
Right, and so you will need to do your check. So you will need to check that the critical point you find in your Lagrangian is a max or a min. And then it's a max or a min here.
Do we need to do a Hessian check? Or
Okay, so
not any critical point works, only if the critical point.
yes.
So for example, if you're looking for a minimum, you have to find the minimum of your Lagrangian.
Yes.
You get points out and then you need to
Yeah.
check is this my minimum, is this my maximum.
So I think the most useful thing is to just do an example. Okay, and that will hopefully also wake you all up. Here is the summary of the method based on this proof. To find candidates for points on the curve at which our thingy is a maximum min, we look for critical points of the Lagrange function. Okay, that's basically what we're doing. So we form our Lagrangian, and we look at the critical points. We find the critical points by doing that. The issue with this method is that it assumes that the constraint problem has a solution. So one thing to do might be to just do a little bit of plotting beforehand to kind of convince yourself that there is actually a solution, because if it doesn't have a solution, obviously this doesn't work. So let's do an example. All right. So yeah.
Well, suppose you don't do your check beforehand. Where
Yep.
exactly does it go wrong?
There are quite a few ways, but basically, I mean, you might not be able to find a critical point, or you might find the wrong kind of critical point. You might be looking for a minimum, but maybe there isn't one, and there's only a maximum. So you do have to reality check your answer, but then you always have to reality check your answer. And one of the interesting things, if you look in economics, and I'm pretty sure in other applications, if we went further with this course, we talk about how it fails and what that can tell you about this system. So it can actually be kind of useful other than just annoying. Yeah. All right, so let's go back to our problem of finding our shortest distance. So we want to here minimize. So we said we're minimizing really the square of the distance subject to g of xy equal to x squared y minus 16 equals 0. All right. So you've got the function. You can put it up here. Here's the method. Go forth. Okay, so you're going to get your three equations. So construct your Lagrangian, get three equations and three unknowns, solve them for x, y, and lambda, and you're done. Oh, except I think, oh no, I did write it down, that's okay. Never mind.
What is f of x? Why?
Anyone want to handle that? What is f of x, y?
X squared plus y squared, right?
Right, it's the thing we're trying to maximize or minimize.
Isn't the thing we're trying to maximize or minimize x squared y equals 16? My question here is like fundamental mathematical notations that I'm confused with.
So go back to the original question. We said we wanted to minimize the distance from the origin, subject to lying on x squared y equals 16. So what we want to minimize is this distance,
Yes.
which is the square root of x squared plus y squared. And we said, well, we're just going to do x squared plus y squared because it's the same thing if we're minimizing.
And that's because if you have this, the x value and the y value, that creates the smallest x squared plus y squared, and it also creates the smallest square root of y.
So what is f of x? X squared plus y squared?
Yes. So if you look at what we've got here, I mean, your f of x is whatever it is that you're trying to minimize or maximize, and your g of x is whatever your constraint is.
So f of x will always be the same if we're talking about minimum distances.
Yeah.
It's a standardized procedure, whereas g of x is the actual function.
Yeah. But you'll see, I mean, this is just an example we're looking at where we happen to want to minimize that. But we're going to look at, I mean, you might want to minimize the cost of producing cars subject to only having however many tons of a certain kind of metal. I feel like you should take out a pencil and actually do this. All right, how are we doing?
Getting there.
Yep. All right, let's talk through it. So we want to form our Lagrangian. So we're going to have our Lagrangian of x, y, and lambda, and that's going to be, so this is our f of x, y, so that's going to be x squared plus y squared, and then our Lagrangian is going to be plus lambda times our g of x, which is this thing here. Okay, So often your Lagrangian looks a little hairy because you're suddenly taking two functions and adding them together. But it's fine. It's okay. Yeah.
So your fxy is always going to be x squared plus y squared, maybe like z squared, right?
No. I mean, it's whatever it is that you're trying to minimize or maximize. So you might have...
In the weekly quiz, we have questions like maximize the volume or like minimize the perimeter.
So, I mean, this is, yeah, so this is used for things like, okay, maximize the volume of, or maximize the surface area of a cylinder subject to the constraint that you only have so much material.
Right.
Or alternatively, maximize the volume subject to some constraint. So this is going to change. I mean, they're both going to change. But the question you're always saying, you've got something that you, some two-dimensional thing, some surface that you want to maximize or minimize, but you're constrained to have it lie on some other function. Yeah. Right. So if you work through this, let's just check that our partials are correct. So we take a partial with respect to x, we get 2x plus 2 lambda xy, and we set this equal to 0. Partial with respect to y, and partial with respect to lambda. Yes? Partials all happening? Excellent. Okay, so what can we conclude? Well, if we have a look at this first equation over here, we could rewrite this as 2x1 plus lambda y. And we see from this that we must have either x is equal to 0 or 1 plus lambda y is equal to 0. Okay, so this one says either x is equal to 0 or lambda y is equal to minus 1. Okay, so you could just dive in and just like straight solve these, but this is 3 equations and 3 unknowns and they're not linear. So using a bit of thought is helpful. Okay, let's think about what either of these two things imply. Well, if x is equal to 0, what would that mean for any of these other equations? Well, it would be fine over here. It would just say y is equal to 0. But if x is equal to 0 over here, then we'd have to have that minus 16 is equal to 0, and that's a problem because it's not. Okay, so this is good news because it means that we can say, okay, well, that's not valid, so therefore we must have that, that this is the case. Okay, so that's nice. Now we know that lambda y is equal to minus 1. Okay, so we actually have, so where can we go from there? We can go to this bit over here. If we plug that in, then we'll get so I think just solve, so here you can solve for lambda. So this one over here, if we do that, becomes 2y squared minus x squared is equal to 0. Okay, and you can carry on working through these. I don't think it's going to be super helpful for me to do that, but you can kind of see the method we're using. So now we've got an x squared here. We can say, okay, x squared is equal to 2y squared, plug that in there, solve for y, solve for x, and then solve for lambda finally. Okay, so I will write out the full working, but you can keep going, and if you do that, you will find that you get x is equal to plus or minus the square root of 2, whoops. So finally what you should find is that you get two solutions, which is kind of what we expected way back at the beginning. We get either x is equal to 2 root 2, y is root 2 and 2, or we can look x is minus 2 root 2, y is root 2. So what has this all told us over here is that at these points, at those 2 points, if we look at that crazy graph that we had at the beginning, at those 2 points on that graph, the distance to the origin is the smallest. Okay. So your mission, when you're going through these notes, presumably after the midterm, is to draw that function properly, see if this makes sense, work through this, and check that you can get those answers. Okay, question?
So we plugged in lambda
Mm-hmm.
as minus 1 over the other. Is it equal to 2y squared plus x squared?
Maybe
I think you.
I could have done something wrong.
No, it's right. It's because it's 2y minus x squared over y, so you just multiply the y out. So it becomes 2y squared minus x squared equals 0.
I think, these terms swap around. Okay. Or just check it. Okay.
My head makes sense.
Okay. Yeah.
From here on, if the first line is f1 of L of xy lambda, and then f2, and then f3, if you were to construct a 3 by 3 matrix to do the Hessian, I think you called it, the check,
Okay.
to see the nature of this critical point,
Yep.
what will we get from that check?
It's a good point. You should find out.
Shouldn't y be yeah.
Maybe?
Precisely because
Sorry. Okay. My bad. I copied it incorrectly. Sorry.
Also, how do you know that, like, we're looking for a minimum? How do you know if these points are minimum? Just drawing the graph. Or would you need to infer the check?
So, I mean, you should technically do a proper check, but you can just, I mean, I would draw the graph. In this case, it's just going to be quicker. Yep. If it's some problem where you don't know what the graph looks like and all of that, then you need to do other checks. But yeah, so good call. You should check. All right. Yeah.
to find z, are we plugging it into Lagrange and then solving for z? Or like, how are you finding the last coordinate?
So this is lambda.
Oh, okay, because it says.
Oh, I'm sorry. That was probably not helpful. That should be a lambda naught. All right.
What does the Lagrangian, like, because that plots a surface, what would it, what's that mean? Does that have any geometric meaning?
So it has geometric meaning. And if I have time, I'll record a separate lecture on it. I probably won't. But it's beyond the scope of what we're doing. But there is, so hidden in this, and part of why I love it, is this huge amount of geometrical stuff happening that has a lot of meaning and is very useful. So if you went on and did kind of like a further course in calculus, or if you did kind of any sort of differential geometry or anything like that, you start to see how all these things tie up. There's a lot going on here. It's not just like this random thing that happens to work. So I would encourage you to actually think through that proof, because there's a lot there. You could essentially, I mean, one could do an entire course on Lagrange multipliers and the geometry associated around there. Sadly, we have 45 minutes. Okay, quick check. Basic method, what the hell, maybe yes? Okay, so if you're here, this is all good. Do some examples. Basically, just do some examples. Yeah.
Can I ask one last question?
Maybe.
You said f of x of y is x squared plus y squared because here the nature of what we're searching for is the shortest possible distance, right?
Yes.
If we had been looking for something different of a different nature, we would use a different f of x of y depending on the nature.
Yep.
But the g of x of y will always be the same because it's the constraint or the thing where we're looking at it in.
Well, I mean, your g is going to change as well depending on the problem. F and g both
but
change.
It's always the same object. It's the graph you're looking at. Whereas the f of x of y, it's the nature of what you're looking at within g of x of y.
Well, it depends how you get g. I mean,
for example, here, if I wanted to try a different...
F and g can both be anything that you like.
For example, I've been looking at the quiz. There's this example of having to, I think, find the dimensions of a box to have its volume be a certain amount. So then your constraint function is the volume equals something. So x, y, z to get the volume of the box equals 32 or something, I think.
Mm-hmm.
And
Okay,
then your
so
f of x would be something else. I don't remember what it was.
Okay.
Okay, so where to go through from here? You could read about problems with more than one constraint, because obviously life is full of constraints. It should be no surprise that this is extensible. You just add on another Lagrange multiplier. So it's not just Lagrange multiplier, it's Lagrange multipliers. Okay? Rinse, repeat, keep doing. Okay, it works for as many constraints as you have, assuming there's a solution. What else? Okay, so these are the kinds of problems. So this is to answer your question. Find A, B, and C so that the volume of this, of an ellipsoid passing through the point blah blah blah, is as small as possible. Okay.
As small as possible refers to the f of x of y, as in the nature of what we're trying to do.
Right. So find the maximum amount, but then we could just say find the maximum values of this bunny, whatever that is, on this thing.
That would be g of x.
F of x, g of x.
And f of x here, it says maximum means that will still be x squared plus y squared.
No, it says find the maximum of this, x, y, z.
Okay.
I feel like you're not hearing me because you're fixed on an idea. What I'm telling you is f can be anything, g can be anything. So find the maximum values of x plus 2y minus 3z, so that's your f, over this crazy thing. Here's a distance again. So here's our surface, and find the distance from the origin to that. Find maximum and min values of this over the curve of intersection of the plane this and this. Okay, f can be anything, g can be anything. All right. Let's take a 5-minute break. Back at 1. All right.
That part. Close your eyes and
Yeah?
yeah.
Okay, then I should do that.
This is not going to be on the midterm, right?
No. Lagrange multipliers are not in the midterm.